Okay, still under the heading of using double angle identities to solve trig equations now. So we're going to apply the knowledge that we know about double angle identities and help us to solve them in trig equations. So the first one is the cosine of a double angle equals a negative sine squared of alpha. So we're going to use our double angle identity, and remember that the cosine of a double angle has 2 or 3 different versions of how we can write it. So we're going to use our context clue here is that the other side is in sine squared. So of the 3 different variations of this, we want to find the variation of the double angle that represents things only in sine. So I'm going to use that third version that's in your key concept double angle identity kit, and that is we're going to substitute in for the cosine of 2 alpha, 1 minus sine squared, or 2 sine squared of alpha. That's going to equal a negative sine squared of alpha. So now we've gotten rid of our double angles. Now we've got to try to figure out how we solve this quadratic style of equation. So we see that these two things are like terms. They're sine squares of alpha, so we can collect them. So what I'm going to do is I'm going to bring this one over to the right, and that means 1 equals, and if I add 2 sine squared of alpha, what we end up with is a sine squared of alpha on the right. So then we want to get rid of our squaring. To undo squaring, we square root. When we square root, it's plus and minus. The square root of 1 is 1 equals, and then we got sine of alpha. So now we want to find the value of alpha. So in order to find the value of alpha, we have to undo the sign. So we'll do the inverse sign. I'm just going to switch the order around. So alpha has to equal the angle whose sine value is either a positive or a negative 1. Whenever we have values of 1 or negative 1, what I would make sure that I would do is I'd make sure I understand exactly where that angle is. And these two are quadrantal angles. So if we get our quadrantal angle on here and our unit circle, I just like to do a little fancy circle here. So there's our unit circle. So where does the sine value equal positive or negative 1? So starting labeling here, we got the order pair 1, 0, the order pair 0, 1, and then I want to get down here because that's 0, negative 1, because the sine values are equal to y values. It's those two angles. In the first rotation, then our solutions are going to be for alpha is pi halves and 3 pi halves. Okay, so that's the first example of using a double angle identity. This time we used it for a sine of a double angle. Remember the decision-making process for this part right here. When you have a double angle for a cosine, you have 3 different forms of it. Choose the form that's going to make your equation the easiest to simplify, which means we want to try to match these other trig functions that are in our problem. The second one is a double angle for tangent. So I'm going to move this over. And I just will group that. Tangent of double angle of beta equals 2 tangent of beta. So there's only one version of a double angle for tangent. So we're going to use our double angle tangent identity. So we got to put in 2 times the tangent of beta over 1 minus tangent squared of beta. And that's equal to 2 times the tangent of beta. So now we have to come up with a way of solving this. Well, everything's in tangent, so that's in at least a positive. But what I'd like to do is get rid of this dividing by, or this denominator of 1 minus tangent squared of beta. So to get rid of it in an equation setting, what we can do is we can multiply both sides times 1 minus tangent squared of beta. And when we do that, we'll reduce those. We'll take it times 1 minus tangent squared of beta. And we'll be left with 2 times the tangent of beta is equivalent to, well, if we distribute 2 tangent of beta, then minus, we can get a minus in there. If we distribute here, it's going to be 2 tangent cubed of beta. Then if we start collecting our like terms, if we move these over, we'll have 0 equals negative 2 tangent cubed of beta. We're going to divide by 0, or, sorry, divide by negative 2. If we divide by negative 2, then it's still just 0 divided by negative 2, or 0 equals tangent cubed of beta. Then we're going to get rid of cubing, and that means we're going to cube root, but the cube root of 0 is still 0, is equal to tangent of beta. And then we want to figure out what is the angle beta whose tangent value is 0. So once again, I'm going to work off this unit circle. I want to keep in mind the major idea behind a tangent is going to be the y over the x. Where do we get a tangent value of 0? That's only when the y's are equal to 0. The y's are only equal to 0 at 0 and pi. And then if we want to consider it back to 2 pi, since it's over that entire domain from 0 to 2 pi, so that means beta could equal 0, pi, or 2 pi. So using some double angle identities to help us solve trig equations is another skill that we're practicing and trying to get ready to solve trig equations. So we've got a lot of different strategies for solving trig equations. The more that we put on, the more complex they become because we have more decisions to make on how we're going to reduce. So there's an example of double angle identities in solving trig equations.